Thanks very much. Um, so yeah, thanks to the organizers. I really regret that I couldn't be there in person, but I really appreciate the organizers and IPAM being so accommodating to me and letting me give this virtual talk. So yeah, so everything I'll talk about today is joint work with Anush Tserunyan. Um, and we we should have this preprint out. We should have it out yesterday, but in fact, Anush already has with one of her graduate PhD students who has now graduated, and another co-author has already submitted another paper that refers to the work that I'm talking about here, and they received a referee report saying that saying that they referenced a theorem from a paper that does not yet exist. So we do need to have this out yesterday. So I do. That's the plan to make a time machine and have it out yesterday. So all right. So let me begin. Uh, so the setting. So X mu will always denote a standard probability space. So we'll see throughout the talk. I'm going to be using an example of free group and the boundary of free group. So we'll see that in a moment. And so that's almost the only example that you really need, with the probability measure coming from the hitting measure of the random walk. But we'll just always be working with a standard probability space. And on this slide, the measure won't really come up, but on the next slide, we'll get to the measure. So E is always going to denote a countable Borel equivalence relation, which has this funky abbreviation C-bar, because it's a lot to say otherwise and to fit on a slide. So a countable Borel equivalence relation on X. So what that means, so it's an equivalence relation. And when we say it's Borel, so it's a standard probability space, means that the underlying sigma algebra is standard Borel. So it's where we took something like the unit interval with its Borel sigma algebra, and then forgot all about the topological structure. We just have the sigma algebra there. And so I'll always refer to the measurable sets as Borel sets. And on X cross X, we'll put the product sigma algebra. And so E being a Borel equivalence relation just means that's viewed as a set of pairs of all pairs of equivalent points. That's a Borel subset of X cross X. And being a countable Borel equivalence relation just means that each equivalence class is countable. And so often the way E is going to arise is it's going to be a relation of being of 2 points being equivalent if they're in the same connected component of some graph that you were handed, or if they are in the same orbit of some group action that you start with. So I'm going to be dealing with treeings of the equivalence relations. So a treeing of E is a Borel graph. So now for the graph to be Borel, I just mean it's viewing the set of pairs of adjacent vertices. That's a subset of X cross X. We want that to be a Borel subset of X cross X. So a treeing is a Borel graph T whose vertex set is X. That's acyclic. So each connected component is a tree. And moreover, we want that the connected components of T are precisely the E equivalence classes. So here I'm sneaking in this notation, which actually I don't think I end up referring to much later. So I called it the connected component equivalence relation E sub T. But that's the point of a treeing, is that we have this measurable way of putting a tree structure on every equivalence class. And okay, so I like to often I'll be working with an equivalence relation together with a treeing. So I'll say it's like an equivalence relation E treed by T. But often I'm interested in actually proving structural results or some kind of structural results of an equivalence relation that doesn't actually make a reference to any given tree, and just knowing that the equivalence relation is treeable, which means that it admits some treeing, it's enough to actually then conclude structural properties. which I find fascinating. So this treeable just means that it admits some treeing. But usually for most of the talk, we'll be dealing with either concrete or something that's already treed. So here's the example to keep in mind throughout the talk. We'll be revisiting this example every slide. So the boundary of the free group. So here, X is going to be what I'm calling the boundary of the free group, viewed as the set of all right infinite reduced words in A inverse, B, and B inverse. So we take a free group on two generators. I'll denote F2. And then we have its boundary, which is the set of all right infinite reduced words in the generators and inverses. And we'll take for our measure the hitting measure for the simple random walk. So it's just it'll be spherically symmetric, and the measure isn't playing a role really at this slide, but we'll get there soon enough. And the equivalence relation on the boundary will be the one coming from the action of the free group on the boundary. The action is just, if an element of the free group is just a finite reduced word, and we can multiply a finite reduced word by an infinite reduced word by concatenate and then reduce, just how you would do multiplication in the free group itself. It's just now it's acting on infinite words. All right, and so the equivalence relation associated to it is a countable Borel equivalence relation. It's the equivalence relation of having the same orbit. So I'll call it E sub boundary of F2. So it's all pairs that lie in the same orbit. And now this is a treeable equivalence relation. We have a very concrete treeing. A treeing of this relation is given by, well, if you think for a moment about what another way of describing very concretely in terms of these infinite words, what it means for 2 points to be equivalent, it means that that there's some common infinite word, and X is just some finite word followed by that infinite word, and Y is some other finite word followed by the same infinite word. So they have this common tail. So this is often called tail equivalence, and a way of defining the treeing is we can use this shift map or the chopping map. So I'll denote that by S. S of X is just obtained from X by chopping off the first letter of X. So X is some infinite word. I chop off the first letter. And then we look at the tree that generates, meaning I connect X to its shift. I connect X to S of X. And this gives me a tree structure. It'll be a 4 regular tree. This shift map is 3 to 1. Now I should say here, I am ignoring, I guess the measure is coming into play here because I am ignoring this countable measure 0 subset of words that are eventually periodic, that eventually just repeat the same finite word over and over. So ignoring that measure 0 set, then we do actually, what I've said here is correct, that every connected component of this is a tree, and the connected components are precisely the equivalence constant. All right, so now let's get the measure more involved. So we'll look at what's called the Radon-Nikodym cocycle. All right, so on the equivalence relation E, there's 2 sort of candidates for natural measures to put on E. They're not going to be probability measures. They'll be general sigma finite measures. There's the left fiber measure and the right fiber measure. All right, and the way that they're given here, I'll say how to integrate a function. Let's say H is some non-negative measurable function. The way we integrate that with respect to the left fiber measure is, well, we're just integrating over X, and then summing over things that are equivalent to X of H of X, Y. So we're going to hold the first coordinate constant, and then sum over the H values where the second coordinate varies over the equivalence class of X. That's the left fiber measure. And on the right fiber measure, we do similarly, but we hold the right coordinate constant and then sum over the left coordinate of things that are equivalent to X. And so then we integrate that with respect to the underlying measure mu on X. So those are the left and right fiber measures. And I'll always work in the setting where E is what's called measure class preserving. And that means that the left and right fiber measures are equivalent in the sense of two measures being equivalent. They have the same null. They have the same null sets. Now, often people work in a more special setting, which is what's called the measure preserving setting, which being measure preserving means that the left and right fiber measures are not just equivalent, but they're actually equal. You get the exact same measures. That would be measure preserving. Measure class preserving is a bit more general. We just want these two measures to be equivalent. And when you have equivalent measures, of course, we can just apply the Radon-Nikodym theorem to get a function, the Radon-Nikodym derivative of the left fiber measure with respect to the right fiber measure. And now this is a function defined on on E, on the set of equivalent pairs, taking non-negative values, in fact, positive values, since the measures are equivalent. And it's called the Radon-Nikodym cocycle. The reason it's called cocycle is it satisfies this so-called cocycle identity. Rho of zx is equal to rho of zy times rho of yx for all E-related points, x, y, and z. This looks mysterious when stated abstractly, but it really not just loses mystery, but it becomes something that you can really work with once you understand the interpretation of what this cocycle is. The interpretation is that rho of yx, which I will denote with, just so that you don't have to remember which coordinate is taking precedence. I'll denote it by rho superscript x of y, and that's really the weight of y from x's perspective. So when we're in the measure, if we were in the literally measure preserving setting, then the Radon-Nikodym cocycle would be the constant one function. Every 2 points weighs the same, and they look at each other and they say, you weigh the same as me, one. So really, rho x of y is just, it can be thought of x always thinks that it weighs one, and we're just giving you the ratio from x's perspective of how much y weighs relative to x. And so now this cocycle equation is literally just saying that, let's see, if y weighs twice as much as x and z weighs 5 times as much as y, then z weighs 10 times as much as x. I mean, there's nothing to it. So now there's the principle called the mass transport principle, which in this setting is literally just stating the defining property of of what it means that rho is the Radon-Nikodym derivative, but it has this nifty name, mass transport principle. It says that if we take any non-negative Borel function, then the integral on the left is equal to the integral on the right. But what is this? What is the interpretation here? We think of this function as this sort of a mass transport function. So it's what we're doing is every point in the space you can think of as a shipping center, and shipping and receiving, maybe a post office of some sort, and our non-negative Borel function h, this mass transport, it's telling us how much the shipping center x is sending to shipping center y, how much mass, say. And of course, this whole setup is that there is no absolute notion of what 1 gram is. Everyone just has its own notion of 1 gram, and we're allowed to compare the relative notions. I'm using the cocycle, but there is no absolute fact of the matter of what 1 gram is. And so when h is this function is h of xy is the amount that shipping center x sends shipping center y from shipping center x's perspective. And so the integral on the left is just is looking at the expected weight that shipping center x sends out. So it's the expected, or mass, I should say, the expected mass sent by a point from its perspective. And on the right, once we adjust by, h of yx is the amount of mass received by x. but that was from y's perspective. So now we have to adjust to get back to x's perspective, which is why we have to multiply by rho x of y. We have to adjust by how much x thinks y weighs. All right, and so the integral on the right is the expected mass received from x's perspective. Since we're multiplying by this cocycle, it actually does give it now from x's perspective. And so the mass transport principle just says that the expected mass sent out equals the expected mass received. All right, let's go to the boundary of the free group. Same example as before. It was generated by this shift or chop map, and that's a 3-to-1 map. You can compute. It's a nice exercise to compute that the Radon-Nikodym cocycle x thinks that s of x weighs 3 times as much as x, no matter what. And so, conversely, if each point x has is the image under S of 3 different other points, and x thinks that each of those 3 other points weigh 1/3 as much as x. So in sort of this forward in this forward S direction where we get 3, and in the other direction we would get 1/3. With these Radon-Nikodym, I mean, when I say it's an exercise, actually, once it's an easy exercise, I guess. Once someone tells you what the Radon-Nikodym cocycle is, then you just verify that it satisfies the defining property. A little more difficult is coming up in a given circumstance. You can either do a guess and check or do something a little bit more systematic. But in this case, you can just check that. And so, okay, that was just telling me how much x thinks that s of x weighs. But now 2 points are equivalent. Remember, the equivalence relation here, it's the orbit equivalence relation of the free group, the equivalence relation being in the same orbit, but that's the same as this tail equivalence. And so a point x and y in the same equivalence class will have the property that there's some m and some n such that s to the m of x equals s to the n of y. So now I have given any 2 equivalent points. I just find that m and n. Of course, you can add the same number to both. Once you have found one pair m and n, you can look at m plus 1 and n plus 1. But it doesn't matter because then the cocycle, the relative weight of y from x's perspective, is 3 to the m minus n. All right, that's a concrete calculation. All right, so the third ingredient that I'll need now is amenability. So here it's the notion of amenability of an equivalence relation, or if one preferred, but it's rather less acceptable to talk about groupoids in public. But if anyone's sort of philosophically, these are all sort of like groupoid notions, which we're taking in the special case of equivalence relations here. So a measure class preserving countable Borel equivalence relation E on x mu it's called amenable if there exists a measurable way of assigning to each point in x a sequence of probability measures lambda n x. So for each n, lambda xn is a probability measure on the equivalence class of x, and I want this sequence to satisfy that that for almost every pair of points of E-related points x and y, if I look at the nth probability measure that x picks and the nth probability measure that y picks, and I look at their distance in L1 norm, just little L1 of the equivalence class. We're not looking at we're not integrating over measure space or anything. Just the little L1 norm of the equivalence class. So just the distance of these probability measures as n goes to infinity goes to 0. So we're assigning a sequence of probability measures to each point of x that lives on the equivalence class of x, such that 2 E-related points are asymptotically selecting very similar, nearly identical measures. All right, and the assignment being measurable just means that if we look at the map that sends a pair yx to lambda n x of y, that should be a Borel. Oops, sorry, that should be Borel measurable for each n. Should take my hand off the trackpad. All right, so going back to our example of the boundary of the free group, this equivalence relation is amenable, and to witness it, for each x, we can look at the sequence of probability measures just coming from taking the uniform distribution on x and its n forward iterates under the shift map. Since the equivalence relation is tail equivalence, if I have two equivalent points, x and y, then as we said before, there's some m and some n, such that s to the m of x equals s to the n of y. And so these sets are going to, for large n, or maybe I'll say k, for large k, these corresponding sets for x and y are going to have huge overlap and only very small symmetric difference. And so they're going to be very close in L1 norm, those uniform measures. All right, so with those definitions out of the way, I can state a result of Scott-Adams, called which Anush and I call the Adams dichotomy. I mean, it's a true dichotomy. It's very very nice statement. So let E be an ergodic countable Borel equivalence relation on X mu. So here, ergodic, I'm just adding this hypothesis to make it a true dichotomy. Otherwise, you have to state things a little more. Well, it won't be a true dichotomy, and you have to state things a little more annoyingly. So, but ergodic just means that if I have any Borel measurable subset of X that's E invariant, or that's a union of E equivalence classes, then it has to have either measure 0 or 1. So let E be an ergodic countable Borel equivalence relation on X mu that is measure preserving. So the Radon-Nikodym cocycle is identically equal to 1 we're not lumpy at all. Just everywhere on the space, everyone looks at it at all its related points and say, they have the same weight. All right, so we have this measure preserving ergodic C bar that's treed by T, and the dichotomy says the following: if E is amenable, then almost every T connected component has at most 2 ends. To be precise, I mean for almost every X, its T connected component has at most 2 ends. And if E is non-amenable, then the space of ends of almost every T component is non-empty and perfect. Perfect meaning it has no isolated points. So it will be a Cantor set if you're in the locally finite case. Here we are allowing for the tree to have countable degree at some places. So, but in any case, it's a perfect non-empty perfect set of ends in the non-amenable setting. And this dichotomy, well, it's very nice. And Anush and I started with this and wondering how, I mean, not only wondering, but sort of saying, well, it's too bad that everything fails miserably in the measure class preserving setting. Because if we just look at our example of the free group, of the boundary of the free group, as I showed on the last slide, it's amenable, but the treeing that we have, it's a 4 regular tree, so it doesn't have at most 2 ends. Every connected component has a non-empty perfect set of ends. So this just fails miserably, and it seemed like, okay, the theory doesn't go any further. And so that's what I thought for a long time. And then Anush and I realized that, wait a second, if you look at things a little bit differently, then you can actually generalize this to the measure class preserving setting. But for that, we need the notion of a non-vanishing end, vanishing and non-vanishing ends. So let E be a measure class preserving countable Borel equivalence relation on X mu that's treed by T. So for each connected component of T, of course, the connected components, by the nature of T being a treeing of E, the connected components are the same thing as the E equivalence classes. So for each T component, we put its end completions. We'll just take that set of that component together with the ends of that component, and we'll give it with the natural topology. It's a compact Hausdorff topology. In fact, compact metrizable topology. All right, just the topology. I'm saying it's generated by all half spaces. It just half space. I mean, you pick a half spaces. You cut at one edge of the tree, and that leaves you with 2 connected components. Pick one of the connected components and take every vertex there together with every end that is represented by a ray through that half space. Or through that component. So, okay. All right, so an end of a tree is called vanishing if, or maybe we also use the terminology cocycle vanishing or Rn cocycle vanishing, but it's vanishing from the perspective of this cocycle if literally when I take the limit in this topological space of the, well, I'm only going to take the limit through approach the end C through vertices, because I only have the Radon-Nikodym cocycle is only defined on vertices. But if I take the limit as y approaches C through this equivalence class of the weight of y, always looking from x's perspective, then the limit is 0. And otherwise, C is called non-vanishing. So sort of terminology I think makes sense. Okay, one thing here is that here x was, it seems like this notion depends on which perspective you're taking from x, or if I move to an equivalent point z, what happens? And the answer is no, nothing changes. This notion of vanishing or non-vanishing is independent of the choice of base point. So if we have 2 points z and x that both belong to the same equivalence class, then the end will be vanishing from z's perspective if and only if it's vanishing from x's perspective. That's just because of this so-called cocycle equation. But the difference between rho z of y and rho x of y, or they only differ by a constant ratio, namely the ratio of whatever rho x of z is. So one limit being 0 is the same as another limit being 0. So it's nice that it's this sort of, even though we defined it in terms of choosing a base point, it's a base point free notion. All right, and in the measure preserving where our Radon-Nikodym cocycle is identically equal to 1, every end is non-vanishing. So non-vanishing end and end in the measure preserving setting mean the same thing. All right, let's look at the boundary of the free group. We're in the decidedly non-measure preserving setting. For each point in our boundary, the forward end of this tree where we connected each point x by an edge to s of x. So if we keep following s, we're going to be going towards this forward end, this limit of s to the n of x. And this will be a non-vanishing end because as we computed this, to prove that an end is vanishing, you need to actually prove that this limit is 0, and the limit meaning topologically. I want to make it, I guess, stress that I don't mean the limit just along the geodesic from x to the end. I literally mean that, for every epsilon, I can find a neighborhood of the end, meaning a half space containing the end, where rho x of y is less than epsilon for all y in that half space. But so that's to prove the limit 0. But to prove that it's non-vanishing, you just need to exhibit one sequence where the cocycle is non-vanishing, of course. And so here's the sequence, s to the n of x, because rho x of s to the n of x is 3 to the n, so it's not going to 0. So it's a non-vanishing end, this forward end. And in fact, if you think about it for a moment, that's the only non-vanishing end of that connected component. Just because if I take any other end, basically the geodesic from that end to the ray from x to c sub x, if I take deep enough edges along that geodesic, they determine the corresponding half space that contains this other end is going to have very small cocycle from x's perspective. As we go deeper, that half space is going to be much further away. So said differently, we said that if we have x and y in the same component, then I can find an m and an n such that s to the m of x equals s to the n of y. Well, once I fix my end, say eta, that's other than this forward end, then as long as I take a half space, a deep enough half space, close enough to eta, then the m for x won't be changing, but the n for all the y's in that half space will be at least like 1 million, as long as I've chosen my half space deep enough. And so then we know the cocycle there is equal to 3 to the m minus 1 million. So it's going to 0. We can make it as small as we want. So there's only one non-vanishing end over here. And so, well, in each component, there's one non-vanishing end. And so this notion is what allows us to do this generalized Adams dichotomy. And so we actually do get a statement that truly generalizes Adams' original theorem, because remember, in the measure-preserving setting, an end is the same as a non-vanishing end, whereas in the measure class-preserving setting, we have to make the distinction. So let E be an ergodic measure class-preserving countable Borel equivalence relation on X mu that's treated by T. So the dichotomy is the same. If E is, except with the word non-vanishing appearing, if E is amenable, then almost every component has at most 2 non-vanishing ends. And if E is non-amenable, then the space of non-vanishing ends of almost every T component is non-empty and perfect. So, well, maybe there's one more result on this slide that is related that I do want that I'll put up in a moment. So, as I said, this notion of vanishing end, we wanted this limit to be taken just in this topological space, not just along the geodesic to the end. But you can also ask, well, what happens along the geodesic? And so we actually are able to prove the following theorem, that in all cases, every vanishing end is what we call geodesically cocycle finite, or geodesically Radon-Nikodym finite. If I sum the weights of all vertices on the geodesic from X to this vanishing end eta, then this is summable. So it's sort of the geodesic itself has finite weight from X's perspective, and from anyone having finite weight is another base point free notion. It just, here we chose the base point to then choose the geodesic, but yeah. So this is the statement, which was somehow the proofs of both of these. So we have 2 different proofs of the dichotomy. One using this mass transport principle that I had on the second slide, or the second slide, and another using what we call the paddle ball lemma, which I think that's this next slide is on. Yeah, the paddle ball lemma. So the paddle ball lemma is going to be something that's purely combinatorial and that has nothing to do with Borel equivalence relations or anything. So if you've fallen asleep so far, you can wake up. And I think this is maybe just an interesting thing that came out of this project that was independent. It's sort of like it feels very closely related to what's called the ping pong lemma from group theory, but it's not. And I've asked many people, and no one's either seen it before or been able to deduce it from the ping pong lemma. So it just seems to be a new sort of combinatorial ping pong style lemma. And we use it to prove the dichotomy for the amenability half of the dichotomy. So the crux of this amenability half of the dichotomy comes down to the case where the treeing T is generated by a single function f, just like how the treeing on the boundary of the free group is generated by the shift map. So when I say it's generated, I just mean it's generated by f means that T is a tree where points are x is always adjacent to f of x. That's the edge set. And so in that case, the goal is to prove that well, you have this forward end, that if you keep applying f, you get towards this forward end, which is going to be in most cases, like in the boundary of the free group, non-vanishing end. And then the goal is to then show that, okay, what happens to these backward ends? And we want to show, well, there are 2 possibilities. One is that there's sort of this measurable way of choosing a single backwards end for each one backwards end for each class, and so then you have this forward end and then this distinguished backward end as well, and that's and then it's very easy to show from there that every other end besides those two would have to be vanishing. But then sort of the most difficult case comes when there is no measurable way of choosing a backwards end, and then you still need to show then that every backwards end is vanishing. And to do that, we need this combinatorial lemma. Well, one of the proofs that we have uses this combinatorial lemma, this paddleball lemma. So the paddleball lemma is stated as follows, and I apologize, I usually do handwritten slides, in which case I would much easier have been able to do pictures of this, but my pen for my iPad broke, so I may be embarrassed enough to bring up something I did on like Microsoft Paint with a with a trackpad, but it really looks like a child did it. So the paddleball lemma says the following. So let's let T be a tree on a vertex set V with a distinguished end, like C plus. So we can think of the way we're going to apply it is when the distinguished end is this forward end coming from the function f, applying powers of the function f. And suppose that now we have a collection sigma of permutations of V. So they're just pure mutations. I'm not assuming they're tree automorphisms or anything. They're permutations. They do satisfy the following two properties, though. So we have this collection sigma of permutations of V, satisfying that for every vertex of the tree, the following holds. So here I'm using this interval notation to denote like the geodesic between 2 points or between a point and an end in the tree. So another way of saying one is saying that V lies between sigma inverse of V and the distinguished end for each sigma in my set of permutations in capital sigma. So V lies between that. So sigma inverse is sort of moving away from this distinguished end, this C plus, whereas sigma, positive powers of sigma are moving towards the distinguished end, are moving vertices towards the distinguished end. And the second is the other important thing, is that if I take any two distinct permutations, sigma and tau, from my collection, then V lies between sigma inverse of V and tau inverse of V. So what it's saying is that we know that sigma and tau, when you apply forward power or positive powers, it's going towards the distinguished end. And when I apply negative powers, it's moving away. But now I want saying that V lies between sigma inverse of V and tau inverse of V just means that sigma inverse is choosing a different direction to move backwards than tau inverse. So this is where the picture would be nice. It is a simple picture to draw. I hope this description people maybe have see the picture. And so one of the important things here that did I go away from full screen? One of the important things here is that this is holding for every vertex V, not just for some vertex. So for every vertex, we have this geometry that this is what's happening. So it's moving every vertex towards the distinguished end and each element of sigma, and every vertex away, and distinct elements of sigma are moving them away, the inverses are moving away, and distinct sigmas and taus, their inverses are moving away in different directions. All right, and the conclusion is that sigma freely generates a free subgroup of the full permutation group of V, and the action of the subgroup generated by sigma on V is free. So this is what we call the paddleball lemma. It's not difficult to prove. I think if anyone sits down and sort of thinks about how to do it, they would be able to do it just drawing a few pictures. Maybe the novelty here is coming up with the statement. I had no idea that something like this, one, would be useful, and two would be true. So, but it is easy to prove once we formulate it. And it's exactly what we needed to sort of apply this to this amenability half of the proof when we have our tree generated by a single function. Okay, so this lemma, I'm not going to say anything more about the proof, of that, let me see, what do we, oh, okay. So the only other thing, and how much more time do I have? Am I, okay. So I probably end early, but I do have enough time to maybe mention some other related results that came out of this project, and also the part of the motivation for the project. Because as I mentioned at the beginning of the talk, I am really interested in understanding structural properties of the equivalence relations themselves, and sort of just knowing that the equivalence relation is treeable, then you actually get to say some interesting structural it has interesting structural consequences for amenable subrelations or maximal amenable subrelations. And sort of the proofs of the results I'm about to state are really along the lines of well, it's the same flavor. We still do use the statements don't require a tree to be fixed, which is what I like. The proofs in the end, though, do. You say fix a tree, and then you do some analyze how the Radon-Nikodym topography of the equivalence relation, how it relates to the tree. But here, let me give a sort of a taste of what we are able to show. And these are things that were proved in the measure preserving setting. I'm attributing it to Adams. I don't know if it's not, as far as I can tell, explicitly stated in Adams, the things I'm about to write, but somehow things like similar to it were stated. And also, I should also probably attribute some of it to there are actually a host of names that I could put here. I think Adams is definitely like the one required one, but then there are variants of different proofs of some of these results in the measure preserving setting. Some using this notion of cost of equivalence relations, some using some probabilistic percolation type ideas. In any case, to state it, I'll need this notion of smooth versus nowhere smooth. So, sort of in the measure preserving setting, what I'm calling smooth would be the same thing. It coincides with just every equivalence class being finite. But in the measure class preserving setting, instead of being the equivalence relation being finite, you have to take into consideration the cocycle. So it's actually the equivalence classes will be cocycle finite. So here, a measure class preserving countable Borel equivalence relation is called, well, almost everywhere smooth. So now when I'm applying the cocycle to a set, I just mean viewing rho superscript x as a measure. So it's just how much does x think that its equivalence class weighs, meaning sum over all elements of the equivalence class over all y in the equivalence class of x, rho x of y. So it's smooth if this is finite, almost surely. And nowhere smooth if every equivalence classes are, almost surely the equivalence classes are cocycle infinite. So in the measure preserving setting, that would just mean literally infinite and literally finite, but here we have to say cocycle infinite and cocycle finite. Okay, so the theorem of Adams in the measure preserving setting that we extend to the general measure class preserving setting is as follows. So let E be a measure class preserving treeable countable Borel equivalence relation on X mu that, and once again, to make it easy to state, I'm assuming ergodicity. So it's ergodic and non-amenable. Then, first of all, each nowhere smooth amenable subrelation of E is contained in a unique maximal amenable subrelation of E. So here, all these notions have nothing to do with trees. It's just literally intrinsic properties that I define totally in terms of equivalence relation. So if I take a subequivalence relation, I can look at and ask whether it's nowhere smooth. So we want that it's cocycle infinite every class or almost every class. And we want it to be amenable. And the statement is if I have any nowhere smooth amenable subrelation, it's contained in a unique maximal amenable subrelation of E. So I can't have two different maximal amenable subrelations that contain this nowhere smooth subrelation. And so it's sort of saying that it's a sort of if you philosophically if you put if you fix a treeing, then sort of philosophically what's going on, it's a sort of transversality statement, which is saying that maximal amenable subrelations are sort of transverse, or in some sense a type of orthogonality, but sort of the way. So these subrelations don't have to actually have anything to do with the tree, right? The tree is just some auxiliary thing that exists by hypothesis, but the subrelation, each equivalence class, it's going to be distributed throughout the tree in some crazy way, not a connected subset of vertices or anything, but sort of at some weird large scale, in some large scale asymptotic way, these amenable ones are sort of do have some kind of either parabolic or loxodromic / hyperbolic behavior that each class sort of looks sort of like at some large scale like that. But so what this is saying is that distinct maximal amenable subrelations are sort of transverse. And a similar, and very along these lines, we have number 2, which it says that every maximal amenable subrelation is almost malnormal. So it's another instance of this transversality of distinct amenable subrelation. So saying it's almost malnormal means that if I take so here phi is supposed to be a bijection. So if I take a measurable bijection where each point x is E related to phi of x, but not F related to phi of x, then this, then we can think of phi as some inner automorphism of E. This is another case where sort of the groupoid perspective, everything's sort of, this terminology of almost malnormal comes from group theory. So here's a natural extension to groupoid theory. But it's saying that if I now take this bijection phi that's in E minus F, or whose graph is in E minus F, then when I apply that inner automorphism of E to F, it's the intersection with F is almost everywhere smooth. So being smooth is a smallness. It's saying that the classes are cocycle finite. So in group theory, malnormal would subgroup H of a group G being malnormal would mean if I take some element of G that's not in H and I conjugate H, then being malnormal would mean that conjugate has trivial intersection with H. Being almost malnormal would mean that the intersection is finite. And so here, this is sort of being cocycle finite is the correct notion in this general groupoid measure class preserving setting. Okay, I've said the word groupoid one too many times, I think. So I'll end there. Thank you very much.